Okay, so thank you very much. So first of all, I would like to thank the organizers for inviting me to speak here. So it's a great pleasure to be at this wonderful place. So today I'm going to talk about work that I've done in collaboration with Miriam Svetic and Antonella Grassi, as well as two students from Penn, Hernan Piragua and Peng Song. And I'm also going to talk about two works in progress. So one work in collaboration with three students from Bonn, Demian Mayorga Peña, Paul Ullmann, and Jonas Reuter, and another work in collaboration with Washington Taylor. Okay, so the topic of my talk is the abelian sector of F-theory. So let me start with a very brief introduction into the subject. So F-theory is really a certain way to treat a setup of a non-perturbative setup of back-reacted PQ7 branes in type 2B string theory on non-Calabi-Yau geometries with regions of large string coupling. And the F-theory language of this non-perturbative setup is basically the geometry of a nice elliptically fibered Calabi-Yau manifold. So in certain contexts, it's actually also useful to think about F-theory as a limit of M-theory on T2, where the volume of this true torus has been taken to 0. Or equivalently to say that F-theory on S1 is the same as M-theory. So certain setups of F-theory are actually dual to the 8 times the 8 heterotic string. And again, other setups are dual to the SO32 heterotic string. And I think we will hear much more about this nice dualities in the talk of Lara Anderson. So the upshot of this slide really is to show you that F-theory in some sense is really in the center of the web of string dualities, which makes it an extremely exciting subject to study. So you can also use F-theory to engineer effective theories. So, and then this means that the geometrical data, like the Calabi-Yau geometry and whatever you want to put here, G-flux, etc., that this gets translated into the physics of an n=1 effective supergravity theory in 6 or 4 dimensions. So actually we have even heard in the beautiful talk of Kumran Waffa on Monday that you can even use F-theory for classifications of 60 1,0 SCFTs. So now the key point is that since F-theory is a non-perturbative, describes non-perturbative string vacua, they have novel features. Yeah, and this means that also the effective theories are different from those you obtain in perturbative string compactifications. And this has actually been used successfully in the past for constructions of models of particle physics and cosmology. And so this was first initiated in the local model building approach by Beasley, Heckman, Waffa, and Donagi, Weinhold, and then later completed in the global models. And there has been a lot of work in these two fields. So the goals of this talk is really to develop and extend this nice geometry physics dictionary that is that underlies F-theory. So on the geometrical concept I want to talk about today is the arithmetic of elliptically fibered Calabi-Yau manifolds, in particular the model Bay group of the elliptic fibration. And I want to relate this to the abelian sector of the F-theory effective action. So, and although this principal correspondence has been established by Morris and Waffa in the early days of the theory, the abelian sector has been rather unexplored, in contrast to the well-studied non-abelian case. And only recently, with some exceptions, there has been a lot of progress on understanding this correspondence, and basically most of these papers here were written in the last 1 or 2 years. So the outline of my talk now is as follows. So I want to provide a systematic construction of abelian sectors in F-theory. So first of all, I want to show you how to engineer the general rank n abelian sector in global F-theory compactifications. And I would like to exemplify this construction at the end, the geometry realizing the rank 2 sector. And then I want to develop a toolbox to study these interesting geometries. And I want to use this toolbox to extract the matter spectrum in 6 dimensions, also in the presence of non-abelian gauge groups. And then I want to show how to extract Yukawa couplings, 4D chiralities, which will make it necessary also to talk about G-flux. And then in the third part, I want to talk applications. So I want to apply this toolbox to the theories, to the geometries realizing rank 3 groups. And I want to apply it to elliptic curves and toric varieties. And last but not least, I want to talk about the moduli space of F-theory and enhancements of U1s. So as a very brief summary of F-theory, let me just show you this slide. So F-theory is some dictionary between the singularities of the elliptic fibration of a Calabi-Yau manifold and setups of intersecting 7 branes. So if you have a Calabi-Yau manifold that is elliptically fibered over a base B, then codimension 1 singularities of this elliptic fibration correspond to the presence of 7 branes and gauge theories living on these 7 branes. So in general, then, you can have intersections of 7 branes at codimension 2 in this base, and this corresponds to the presence of matter in F-theory. So there's one subtlety. When going down to 4 dimensions, we only obtain chiral matter if there's some G-flux present. So, and then generically, if the space is 3-dimensional, we have Yukawa couplings at codimension 3. So now let me come to the actual subject, the appearance of U1 symmetries in F-theory. And in order to understand how U1s arise, let's first step back and recall how non-abelian gauge symmetries are constructed. So if you have a elliptic fibration, you can specify this elliptic fibration by writing down this Weierstrass form. And then you might see, by investigating this fibration, that there's a singularity at codimension 1. So now the first step then is to ask how serious is the singularity. And this, the severity of the singularity is encoded in the singularity type, and which is specified by the orders of vanishing of Fg and the discriminant delta along this divisor. So, and then the singularity type translates into the structure of the tree of P1s that you obtain in the resolution of this singularity. So here's one particular example, the resolved I4 fiber, and you get 4 P1s that intersect in the Dinkin diagram of the affine SU5 Lie algebra. So now, having this geometrical description, gauge symmetries arise as follows. So the Cartan generators arise in the KK reduction of the M-theory 3 form along the 1-1 forms that are dual to these P1s. So, and then in addition, you also have M2 brane states that wrap these P1s, and in the limit of vanishing volume of this 2 torus, these states become massless, and the gauge symmetry enhances accordingly. And you have a non-abelian group. So now the basic idea of U1s in F-theory is that you still want that U1s should come from a KK reduction, like the Cartan generators of the non-abelian group, but you want to forbid this enhancement by the light M2 brane states. So this means that you can only consider fibrations that have I1 fibers at codimension 1. And then the statement is that these 1-1 forms that support these U1s actually correspond to rational sections of the fibration. So in order to understand what a rational section is, let's first recall what a rational point is. So if you have an elliptic curve E and with a 0 point, then a rational point on this elliptic curve is simply a solution to the Weierstrass form where the coordinates of this point take values in the specified field K. And then, since an elliptic curve is also an abelian group, you can define a group law on these points, and this turns the group of rational, the set of rational points into a group, which is the model Bay group of rational points. So now when you have such a curve...
To go back to
yes?
Did you explain why 1-1 forms correspond to rational sections?
No, I'm not yet there. I'm coming there. So this is on the next slide. So when you now have this elliptic curve, and you with a rational point, and you put it in a fibration, this means for every point in the base, there's a corresponding map. You can construct a map that maps this point in the base to the rational point on the fiber. And then by following this point over the entire base, you basically get a second copy of the base inside this space of the fibration. And this actually defines a new divisor class in the total space of the Calabi-Yau. And the class of this 1-1 of this divisor is dual to the 1-1 form that supports the U1 gauge field. Okay. So now let me talk about the structure that is imposed upon the elliptic fibration due to the presence of this rational point. So if you just take the Weierstrass form and you plug in this rational point into this Weierstrass form, you get a particular relation between f and g. So this is trivial. But now this relation allows you to factorize or to write the Weierstrass form in this factorized form. And then you see that this Weierstrass form has a singularity at the locus, at a codimension 2 locus where these two constraints here vanish. And the Weierstrass form becomes singular. So now the thing is, when you resolve this, singularity, you actually obtain an I2 fiber. And you have this I2 fiber at codimension 2 in the base. And so this means that there has to be matter in F theory. So you see that the presence of a section implies that there's automatically charged matter under this U1 symmetry. And you can also see that there's no additional singularities, so the I1, you only have I1 fibers at codimension 1. Okay, so now the task is to provide an explicit construction of these elliptic curves with rational points. And this means that I want to solve these constraints that are imposed on the functions f and g in the Weierstrass form, and I have to provide a resolved Calabi-Yau elliptic fibration in order to make sure that the model makes sense. And addressing these 2 points will require the departure from the Weierstrass form, as I would like to argue next. So if you have an elliptic curve with a 0 point and a number of rational points, then this curve has a canonical embedding in some weighted projective space. And this works as follows. So if you have these points, there exists this line bundle M of degree n plus 1, which is just the sum of all the points on the curve. And then the embedding space of this elliptic curve is determined by requiring that this line bundle M is just a pullback of O1 on this ambient space back to the elliptic curve. So let me walk through this at the hand of one example. So if you have a curve with 2 rational points, this bundle is degree 3. This means there are 3 sections. And these 3 sections are the P2 coordinates of the ambient space. And then you can see that these sections actually obey a relation at order 3. And this means that this curve is embedded into P2 as a cubic curve. So now let's impose the existence of P, Q, and R. This means that E cannot be generic, so that the constraint for E has to factorize in such a way that, for instance, the intersection of E with the hyperplane U contains these 3 rational points. So however, it turns out that E is not generic in P2, but in a different ambient space, precisely in the ambient space that is P2 blown up at the points Q and R. So this means that it's a generic Calabi-Yau in dP2. So what I have just shown you is that E in the rank 2 model Weil case is the generic Calabi-Yau in dP2. You can go through the other cases and you obtain this nice list. So you get the Tate form. For 1 point, you get the blow-up in P1, 1, 2. And then for 3 points, you realize that the curve is no longer a hypersurface, but it's a complete intersection. And for n bigger than 4, or bigger equals to 4, you actually realize that not even this is enough, but the curve is just a Pfaffian variety, or it is only determinantal, as has been shown by Koh, Stillman, and Eisengut. So there are some key properties that I would like to highlight here. So first of all, elliptic fibrations constructed with these curves, these ambient spaces, are smooth. And in the most general case, actually, the 0 section happens to be non-holomorphic. So, and nevertheless, these backgrounds define valid F-theory backgrounds. So now let me discuss the toolbox for studying these geometries. Let me illustrate this for the dP2 elliptic fibrations. So all we have to do to construct an elliptic fibration is again to write down this cubic, and now to lift the coordinates on the P2 fiber to sections of certain line bundles on B, and also the coefficients Si. And then you can actually see that the Calabi-Yau manifolds, these elliptically fibered manifolds, are completely specified topologically by the choice of 2 divisors that are associated to these coefficients S7 and S9. And these degrees of freedom can and should be varied. So actually, when you are on a specific base like P3, you see that these 2 divisors are specified by 2 integers. And these integers can take values at the integral points in this region. So each point in this figure corresponds to one particular topologically distinct Calabi-Yau X. So, and actually, in physics terms, this means this figure is actually the space of all 4D F-theory vacua for fixed fiber in dP2 and over the base equals to P3. And we can indeed construct all these models and study the entire family of F-theory compactifications. So you don't talk about just one model, but you can write down formally that apply for this entire family of F-theory vacua. So let's continue with working out the physics of these models. So, and let's look now at charged matter. So as I have tried to argue at the beginning, there's charged matter at a certain codimension 2 locus in the base. So the problem is now that this locus is a highly reducible variety with many components in general. However, we are interested in the individual components of the irreducible components of this locus because they correspond to the individual meta loci. And in order to find these irreducible components, we actually have to deal with ideal techniques because these irreducible components are only described in general by prime ideals. So they are not complete dissections, they're described by some complicated ideals. So the problem is now that it's computationally very involved to find all the associated prime ideals to this meta locus because these are polynomials in general of a very high degree. So we need some sort of bootstrap in order to extract still these meta loci. And the good thing is that some of these meta loci have a nice geometry and physics interpretations and are thus easier to find. So for instance, there are meta loci located at the loci where the sections are ill-defined, or there's meta located where additional constraints are met that correspond to multiple U1 charges. So, thank you. So indeed, you can use these techniques now to derive closed formulae for the 60 meta multiplicities, and you can do this for entire classes of F-theory vacua over any base B. So here's just an example. Again, the curve in dp2. I've chosen a specific base in B equals 2p2. This is the charges, and this is the corresponding meta multiplicities. And you can see that this explicitly depends on these parameters N7 and N9 that specify the elliptic fibration, and you have these nice closed formulas. Then you can go on and check consistency of the theory, like 60 anomaly cancellation. You see that the theory actually makes sense. Okay, so now you can even go further and systematically add non-abelian groups. This can be done by using TORIC tops or extending the Tate algorithm to other elliptic fiber types, which has been recently been done for the fiber in P112. And you can still apply these techniques to obtain the full 60 spectrum. So for instance, in the DP2 case, with an additional FU5, you can still write down the full 60 meta spectrum, including multiplicities. And then also codimension 3 phenomena can be analyzed. And again, in order to determine whether meta loci intersect, you have to use their corresponding prime ideals. And indeed, in the DP2 case, you can check that in the case with an SU5, for instance, all gauge invariant Yukawa couplings are indeed realized geometrically. So, okay, so this, how much time do I have? Okay, so there's 5 minutes. Okay, so then probably I have to fortunately skip this slide here, but there is a beautiful.
You can take another 3 if you wish to elaborate most of the
Okay, so there. So if you're on the Calabi-Yau fourfold, there's an additional degree of freedom that you have to add, which is the G-flux. So G-flux geometrically lives in a certain cohomology group. Here I only focus on the vertical G-flux, and this requires a computation of the primary vertical cohomology of Calabi-Yau fourfolds. And the good news is that this can again be done for examples. For instance, for the elliptic curve in DP2, you can explicitly compute H22 vertical of this Calabi-Yau over base equals to P3. So, but however, there's one subtlety when talking about G-flux and F-theory, and this is the fact that G-flux is actually an M-theory concept. So it should be properly addressed in M-theory. So, and the strategy that we are using here is to use the duality of F-theory on S1 to M-theory. So in the 3D effective action that you obtain, all the information about the G4 flux is actually encoded in the Chern-Simons terms of the effective theory, so about the vertical G4 flux. So now MF-theory reality for these Chern-Simons terms means that these M-theory Chern-Simons terms have to be related to the F-theory Chern-Simons terms, and it can be shown by other arguments that I don't have time to discuss, that these depend on the 4D chiralities of F-theory. So it's a beautiful story, and I'm happy to talk to you about this more in private. And you can use this relation then to compute 4D chiralities on the one hand, but also to derive conditions on G4 flux for suitable F-theory compactifications. So this is the toolbox, and now let me come to some applications. So application 1, elliptic curves realizing 3U1s. So in this case, the elliptic curve is a Calabi-Yau complete intersection in the blow above P3. And again, now applying this program, we can show that all elliptic fibrations of this curve over basis B are classified. There's a nice correspondence between F-theory vacua and polytopes. You can work out the meta representations. There are 14 of these. And I would like just to highlight one piece here, namely that there's a very miraculous structure of singularities of this elliptic fibration that yields to the presence of tri-fundamental meta representations. Then you can go on and work out 60 meta multiplicities and check that anomalies are cancelled. So this is just to show you how these formulae look at the end. So here you have the 14 representations. You have the meta multiplicities all parametrized in classes of the base. And at the end of the day, you can add all these classes, these expressions up, and you can put them in the anomaly equations, and you get a vanishing result at the end. So all this algebraic geometry actually yields well-defined effective theories. Okay, so as a second application, let's consider elliptic curves that are hypersurfaces in 2D toric varieties. And let's look at those that are specified by the 16 reflexive polytopes. And let's apply, again, the program that I've just shown you to elliptic curves in these ambient spaces. So again, let's classify all elliptic fibrations. This is of these curves over a given base. This is possible. Then determine the gauge group, and then work out the meta spectrum, meta representations, multiplicities, and the geometric Yukawa couplings. So here are the results. So on this axis, I have the model Weil rank. Here's the total rank of the gauge group. And you see that we have models with up to rank 3 model Weil group. There are models that have model Weil torsion, so non-simply connected gauge groups. And there are also models that don't even have a section, but only a multi-section, and where you have to use techniques involving Jacobian fibrations. So let me just point out two features of this figure. So this figure is nicely symmetric around the rank 3 line. And this is actually nice because the polytope is on top of it, and the polytopes below this line are actually dual to each other, so they're related by mirror symmetry. And there's a nice sum rule, namely that the rank of the gauge group of the polytope and of its dual always adds up to 6. So, and another thing is that all these polytopes here are connected by extremal transitions in the fiber, which means in the effective theory a Higgsing, and you can get all these theories by starting from these 3 red polytopes. So, last but not least, the third application, and that's the modular space of M theory. So, and it turns out that it is crucial to have elliptic fibrations with higher rank model Weil groups for the global understanding of the modular space of F theory. So because you can ask this question, can we tune the complex structure of the Calabi-Yau to always enhance U1s into a non-abelian group? So actually it turns out that in the rank 1 case, when you have 1 U1, this is true. So whenever you have a model with a single U1, this always can come from the Higgsing of an SU2 on a Riemann surface on a genus G curve. And so if you have a model with U1, you can always do this tuning in complex structure modular space. So however, in the rank 2 case, the story is a little different because there are different types of possible enhancements. So how does this work? So if you have so what do you have to do in order to enhance U1s into non-abelian groups is you have to reduce the model Weil rank by merging these rational points with the origin. So here's the cubic, we have 3 rational points. So let's make P and Q agree. So this means that the distance between these points has to be set to 0. And then let's also make the point R agree with the point P and Q. And this means that the second distance has to be set to 0. However, we see then in this case, this elliptic fibration takes a very particular form. This cubic here is completely degenerate. And this means that in these tuned elliptic fibrations, there are codimension 1 singularities automatically built in. So for instance, when these polynomials lambda 1 and lambda 2 are set to 1, then there is at the locus where this polynomial here vanishes in B, there is an I3 singularity of this elliptic curve. Yeah, and this means that these U1s here have actually enhanced into an SU3 gauge group. So there's another case. So when you set this polynomial here to 1, then you see that the fiber here becomes I2 whenever these polynomials lambda 1 and lambda 2 vanish. So this corresponds to an enhancement to SU2 times SU2. However, in the most general case, when all these polynomials can be non-vanishing, the generic unhixing pattern or enhancement pattern will be to SU3 times SU2 times SU2. Okay, so this is now the summary of my talk. So I tried to show you how to construct elliptic fibrations with higher rank model Weil group. I developed a toolbox to analyze these models, to extract the 6D matter spectrum, 4D Ukavas using ideal techniques. Then I showed how to compute 4D chiralities by NG flux, by cohomology computations, and by developing flux conditions on G flux and F theory. And then I applied these tools to elliptically fibered Calabi-Yaos in DP2, also with additional gauge symmetry, the complete intersection in the blow-up of P3, and all hypersurfaces in the 16 2D toric varieties. And as a last point, I showed how to enhance U1 squared into non-abelian groups, and I presented that it's not always possible to have a rank-preserving enhancement. So as an outlook, it would be nice to pursue this classification for more than 3 rational points and to investigate the corresponding heterotic duals. Thanks.